Alright, hello everybody. So this will be homework 3, where we will be going through how to simulate a distillation column. So first, to get into the theory of how it all works. So let me just get the shapes in here. Where not what I meant to do, but it's closer to the middle here. So in our distillation column that we're going to simulate, we're going to have 6 trays, such that NT equals 6. However, what we're actually going to have is 2 additional trays, one for the condenser up here, and then another one for the reboiler down here. Got the reboiler, we got the condenser down here. Now, for the purposes of this simulation, we're going to assume we have a total condenser, so that no vapor leaves the condenser, except through the distillate, which we'll be leaving as a liquid. And then down here in the boiler, we also got our bottoms leaving. And then we move this up some. Our feed stage is going to be our third stage. So here's our stage 0, or stage 1, 2, 3, 4, 5, 6. So our feed is coming in at some vapor fraction and at some composition of our component we want to separate. Now for this simulation, the one we want to separate will be the more volatile compound. And when we say volatile, what I mean is we're talking about our alpha values, where our alpha is equal to the phase equilibrium between 2 species. So in this case, our A and our B. Now, what we can do, since this is going to be a binary distillation, meaning we only have 2 components, A and B, is we can redefine Ka, or I mean rewrite Ka as Ya over Xa, because it's the phase equilibrium ratio between the two, saying we got so much of A in the vapor phase compared to so much of A in the liquid phase. Excuse me. And then same thing with B. Let's write that out real quick. YB, XB. Now the cool thing that can happen here is, since this is binary distillation, meaning only A, only B, that means YB has to be 1 minus Ya. And then same thing with XB. So now if we go back up here to our original alpha up here, which is equal to Ka, Kb, we can then substitute those. So we got YA over XA divided by YB over XB. And then we replace the YB with 1 minus YA, XB with 1 minus XA. What happens is we got YA multiplied by XB, which is 1 minus XA, divide all that by XA, multiplied by 1 minus YB, or YA. Then on the left side, we still have our alpha. Now, from here, what we're going to do is we're going to solve for YA. So, multiply by the bottom, got alpha XA, multiplied by 1 minus YA, equal to our vapor mole fraction of A, multiplied by 1 times the liquid mole fraction of A. Now I get Y by itself once again, we got to divide by 1 minus XA. So, what's going to happen is we got alpha XA over 1 minus XA multiplied by 1 minus YA. Now get us our YA, or our vapor mole fraction. So from here, what we need to do is we just need to distribute. So alpha XA stays on this side, 1 minus XA, and then what we're going to do is we're going to combine two steps. This is going to distribute to the YA, and then we're just going to add that to this side. So comes YA multiplied by 1 plus alpha XA over 1 minus XA. And then what we're going to do here is we're going to make this into a fraction by multiplying it by 1 minus XA. So on this side, we got going is YA multiplied by the 1 plus XA multiplied by alpha minus 1. And all of that is over 1 minus XA. So now over here, to get YA by itself, we're just going to divide by this. So on this side now, we got alpha XA multiplied by 1 minus XA. All of that over 1 minus XA times 1 plus XA alpha minus 1. Strange looking alpha right there. Alright, and then if you notice, that cancels out, so we're only left with these two. So that means our function for YA is the volatility times the liquid mole fraction all of that over 1 plus liquid mole fraction times alpha minus 1. Now when we go to plot this, what's going to happen is we're going to have YA on the side, and then XA on the bottom. And then, since we're going to go with a more volatile compound, so that means alpha will always be greater than 1, we're going to get a shape like this, where you got sort of like this hump going on. So now that we got our function for finding our vapor mole fraction, what we can do from here is start worrying about the mass balances up here. What I'm going to do is I'm just going to rename this to a good name for this one. Let's go. Add a new page, and then this one will be talking about our mass balance. So if you recall, in the tower, we have 6 stages. Add 2 for the condenser and the reboiler. Now, if we go back and look at those stages, we're going to see 3 types. Our first type we're going to look at will be the reboiler, or the condenser. So in the condenser, what we got going on is we have a vapor coming in the condenser, and then we have liquid leaving the condenser, and then we also have a distillate leaving the condenser. Remember what I said about this being a total condenser, meaning we don't have any vapor leaving. So, and then go back up here. So our condenser was our stage 7. So that means the vapor is coming from stage 6, and then liquid is leaving 7. So this change in moles of the stage 7 is equal to V6 minus L7 minus the distillate. Now, remember, with distillation towers, we got something called a reflux. So what reflux does is it controls the ratio at which distillate leaves the tower. So for our initial simulation, we're going to assume this is a 2. And so what that 2 means is that the liquids right here at the reflux point is 2 times greater than a distillate. So if we say R is 2 here, that means when we come down here, that means the liquid is 2 times D. Right? So if we were to rewrite our change in mass for 7, you would get V6 minus the distillate multiplied by 1 plus R. So now, if we want to look at our next stage, let's look at the reboiler. So for our reboiler, we have liquids leaving in the form of our bottoms. And then in order for our reboiler to work, it has to have a certain mold in here. And then as it boils, vapor is given off. It's our stage 0. But we also got liquid coming in here. It comes from the stage above it, L1. Which reminds me, for our simulation to work, what's going to happen is this will be maintained at a specified volume. So what that means is we are going to assume we have perfect reboiler control such that this is always at steady state. So V6 will always be equal to L plus D. Essentially making M7 0. Now this is just for our simulation. In real life it might be different, but in order to make that true, we have to have some form of control down here keeping this level constant, or getting it to change based on a certain response. So how to do that is we're going to use a proportional control. So we'll have a certain Kc value where we'll just set it to 20, for example. So what that's going to do is it's going to look at the mass or the moles in here. So look at moles in here. It's going to compare that to the set point. And then the response will be given by Kc multiplied by that difference. Now, keep in mind, this is only the response, so we have another part here to worry about. So, if you go back here, look at our first diagram, where if you look at the entire tower as a mass balance problem, we have a certain amount of F coming in, and then we have a certain amount of D and a certain amount of B coming out. So in order for this to not accumulate anything, D and B have to be equal to F. If we go down here, F has to equal the distillates plus the bottoms. So we rearrange that. The bottoms, this one right here, has to equal F minus D. So and since the bottoms are leaving the reboiler, it's going to be negative. So the change in mass at stage 0 is going to be equal to our feed minus our distillate multiplied by the gain, and then the difference between the current state of the moles and the set point. So, actually, hold on. I think I screwed that up. Yeah, so since the bombs are leaving, the distillate minus the feed. And then add the proportional gain. So now we got our condenser stage, we got our reboiler stage. Now all that's left is to look at our normal trays. So for our normal trays, what's going to happen is we are going to have vapor leave and liquid come in the stage above, then we're also going to have a vapor come in from the stage below, and we're also going to have liquid leave the tray. So, up here, our change in mass at stage I, or change in moles at stage I, is what's going into the tray. So we got VI minus 1, so the vapor from the stage below, plus the liquid from the stage above, subtracting the vapor and liquid leaving the tray. And then for the feed stage, another thing that's to worry about is we're also having feed come in from this side. So the change in mass at the feed stage is also going to have that addition component of the feed. And then from there, so we got our mass, or change in moles, but now we also got to think about is our change in composition. So for example, the change in the amount of XA. So, for example, up here, reboiler, just like how we got our change in mass here, the V6 minus D1 plus R, the composition, so the vapor mole fraction at stage 6 times the vapor flow rate at stage 6 minus the liquid mole fraction times D 1 plus R. And then, so that's for stage 7. So let me go in here, just erase some of this. So for stage 7, you're just adding on that component part, the Y6, the X7. And then reboiler, same deal. The change in M0, X0 regards to time is equal to so for the distillate, the bottom, right there. And then also, I forget something here. Oh yeah, I forgot to account for V0, L1. So minus V0 plus L1 here. Alright, let me just make this here again. Right, so minus F. Everything looks good there. So, for our distillate, X7 times the distillate minus our feed composition, which is our ZF, plus let me think about that. Actually, wait a second. I think I jumped the gun on here a little bit. So for our stage 0, the moles right here is equal to L1 plus, or L1 minus Z0 minus bottoms. So what I was solving up here was I made a little bit of an oopsie, and then this will get into when we start calculating our liquid vapor flows. So ignore that for now. Our mass balance, or the rate of the mole change in stage 0, is the liquids from above minus the vapors leaving minus the bottoms. Let's go down here, get rid of that. So here, X1L1 minus X0 V0 minus X0 B for bottoms. Just realize that should be a Y, not an X, because we're talking about vapor here. So that's for stage 0. Now for the rest of the stages, what we're going to do is go back here. So we got the vapor from below, multiply by that mole fraction, plus the liquids from above times that mole fraction, minus VILI. So, got our YV at stage I, and then our XL at stage I. And now give us our mole fraction there. And then just like how we had to do an addition at the feed stage, we also got to do one here. Which is just the same as every other stage from 1 to 6, except now you just add on ZF. So now we got our DM and we got our DMX. Now you might be asking yourself, why do we define these? Because ideally what we want to do with the simulation is find out how pure our distillate and our bottoms are. So to do that, we got to find DX. And then we're going to run that through a ODE solver to get us a function that can estimate it. So to do that, we're going to be looking at our DMX. Because what's happening here is DMX is actually two functions, MT, XT. And then what we can do with that is we can do chain rule to get this. So DMX equals M times dx dt. Well, we just do dx for now. And then add x times dm. And then all I gotta do from here is solve for dx. So by solving for dx, we get dx equal to 1 over the moles in each stage multiplied by the change in moles of X of A multiplied or subtracted by the molar composition or the liquid composition in each stage multiplied by the change in moles of each stage. So now we got our ODE, our ordinary differential equation here, which we'll solve using SciPy when we get to coding. But now that we have that, now we need to actually start getting values for these V's, L's, V's and D's. What I'm going to do is I'm going to add another page here, go up here, and do a liquid vapor flow. So, if we go back to our original diagram here, what you notice is at stage 3, all the way down to 1, we're going to have to treat differently than stages 4 through 6. The reason is this feed stream here, because the liquid flow rate from 3 to 1 is going to have an additional liquid flow from the feed based on our Q. And same thing with vapor for 4, 5, 6 because of our Q and F. So what we got to do is let's first start with our vapor. So if we look at our very top stage, stage 7, the condenser, let's draw that one more time. Got our VLD. Now remember what I said about having a total condenser. So we got no flow coming out, and then we also have perfect reboiler control, meaning that this level is always constant. So M7 has to be equal to 0. So to do that, we set up our mass balance equation again. We have M7 equals V minus L minus D. So that means our V here has to be equal to L times D. Or not multiplied, add. And then what we're going to call this vapor flow is we're going to call this V rectify, because it's above the feed stage. So what that means is we're also going to have a second vapor flow rate for the flow rates below the feed stage. So for example, down here at the reboiler, draw that there. Got V coming out here, liquid coming out here. We also got our bottoms. So for this V, what we're going to do is we're going to call this one V strip, because that is what's happening in the stages below the feed. Our stripping V. Now remember what I said earlier about the vapor flow rate having an additional component here based on our Q from the feed. So that means the flow rate down here is going to be the rectifying vapor flow rate minus that component here. We go here, it is Vrec minus 1 minus Q, because Q is the percent of liquid in the feed multiplied by the feed flow rate. And then that is what's going to get us our stripping vapor flow. So now that we got that, we got all of our vapor flow rates. So for stages 0 through an F, it is the stripping. And then for stages NF plus 1 through NF minus 1, I should say. That's going to be V strip. And then for NF through the NT plus 1 for our condenser, that's going to be our VREC. Alright, so now we got that going. From here, what we can do is now we're going to be looking at our liquid flow rates. So, what's going to happen here is we're going to have, once again, 3 different cases. So the easiest case to understand is going to be our condenser. And draw that back out. So for this, what's going to happen is our liquid flow rate is equal to the distillate multiplied by the reflux ratio. Because remember, reflux here is just L over distillate. So that's our L7. Now if we look at the reboiler control, or the reboiler, what we can do is L7, this is our reboiler, we got a certain amount of vapor here, got L coming in, we also got our bottoms. Alright, so to get our bottoms flow right here, to figure this out, what we got to do is first we have to go back to that original mass balance equation. Just B is equal to the feed minus the distillate. Now remember, this is under proportional control. So we're also going to have to add in that Kc component based on where our mass is in here. So for example, if we start this tower with say 0.6 moles in here in our reboiler, but we want it at 0.5, it's going to read this as, hey, we are over it, so we need to let more out in the bottoms. So that gives us our bottom flow rate, which in our code we're just going to call L0, because that's a liquid leaving stage 0. And then finally, what we're going to look at is our just nth or I stages. So what's going to happen here is in these stages with these trays, what's going to happen is it looks like this, where we have like some wall here. we got mass, or moles, building up through here, and then whatever is over that wall gets thrown over. So this amount of mass that gets held by this wall here is known as the holdup. So our tray M is our holdup. So that's just the number of moles that will fill this little reservoir here before it starts falling over. Now, another thing to consider about this tray is something called a weir coefficient. Basically saying, like how with a cup of water, the surface tension will sort of keep it from falling over if it's just over the rim of the cup. So that weir coefficient is going to sort of help push this over. So to do that, we're going to give it a little omega symbol here for weir. And then with that, and then the formula for that is this amount of liquid flow is equal to that weir coefficient multiplied by the mass in this stage subtracted by the holdup and that's raised to the 3/2 power. Component I, and then all our trays are going to have the same holdup. So we got our vapor flows, we got our liquid flows, we got our mass balance, we got our DMX, our DX, our DMs, and we also got our function for vapor mole fraction. So the only thing we have left to do for this part is we just need to go through our initial conditions. Now the reason we have to get initial conditions is in order to solve these ODEs, we had to have an initial value, which is why they're called initial value problems. So for our initial moles, and we also need initial mole fractions. We need M initial, X initial. So first, let's just do an X initial because it'll be real simple. For our initial conditions for X initial is we are just going to say each tray has the feed composition. So XY equals E for all stages. Now, this M initial gets a bit more complicated. So MI equals some array for each stage. So M0, what we're going to do is we're just going to say that's at our set point for the reboiler. So let's say M set point there. Now for the condenser, we're also going to have it at some set point for the condenser. Now for stages 1 through 6 is where it gets a little interesting. So like we were going through with the Weir equation, where liquid flow equals Weir M minus M tray raised to the 3/2. If we rearrange that to solve for M, we get L to the 2/3 over Weir L over Weir to the 2/3 plus the tray holdup. And then that will get us our initial flow for the or initial mass in each tray for stages 1 through 6. So that's going to conclude the theory part of this video. In the next part, we're going to go through with collaboratory and just plot this out, show you how it works, and then we're going to be using something called SciPy to get the basically solve for dx, because we can find dmx and dm. Alright, with that, thanks for checking out this video, and I will see you in a little bit.